Imagine a moment so powerful that it created everything you see around you, the stars above, the ground beneath your feet, even the air you breathe. A single instant when time itself began. What if I told you that 13.8 billion years ago, our entire universe, all the galaxies, planets, and life exploded into existence from a point smaller than a single atom? This is not science fiction. This is the greatest story ever told. The story of how our universe and our home planet Earth came to be. For centuries, humans have gazed at the night sky and wondered, how did all this begin? Was there a creator, a divine spark, or was it a blinding flash of energy that set everything in motion? Today, thanks to powerful telescopes like Hubble and James Webb, particle accelerators, and decades of groundbreaking research, scientists have pieced together an astonishing timeline. We now know the universe is approximately 13.8 billion years old. It started with the Big Bang, not an explosion inside space, but the birth of space and time itself. Before the Big Bang, there was nothing. No space, no time, no matter. Everything was compressed into an infinitely hot, dense singularity. Then, in less than a trillionth of a second, the universe began expanding faster than the speed of light in a phase called cosmic inflation. Temperatures were trillions of degrees. Energy turned into particles, and the seeds of everything we know were planted. This documentary takes you on an epic journey from that first unimaginable moment to the formation of our beautiful blue planet. We will explore how stars were born, how galaxies formed, how our solar system took shape, and finally, how life sparked on Earth. You are about to witness the ultimate origin story, one that connects every human alive today to the stars, because we are all made of stardust. Our atoms were forged in ancient supernovas billions of years ago. So sit back, open your mind, and prepare to travel back in time to the very beginning of everything. This is the birth of our universe and Earth. 13.8 billion years ago, our universe did not exist as we know it. There was no before because time itself had not yet begun. All the matter, energy, space, and time that would ever exist was squeezed into a singularity, a point of infinite density and heat. Then came the Big Bang. In the first tiny fraction of a second, 10 to 43 seconds to be precise, known as the Planck era, the laws of physics as we understand them broke down. Gravity, the strong nuclear force, weak force, and electromagnetism were unified. Almost instantly, the universe underwent cosmic inflation. It expanded exponentially, doubling in size countless times within 10 to 32 seconds. This rapid growth smoothed out the universe and set the stage for the large-scale structures we see today. The temperature was an unimaginable YP Kelvin. As the universe continued to expand and cool, energy began converting into matter. Quarks and antiquarks formed, then annihilated, leaving a slight excess of matter. By 1 microsecond, the universe had cooled enough for quarks to combine into protons and neutrons. 3 minutes after the Big Bang, the temperature dropped to about 1 billion degrees. Protons and neutrons fused to create the first atomic nuclei, mostly hydrogen and helium, with traces of lithium. This is called Big Bang nucleosynthesis. For the next 380,000 years, the universe remained a hot plasma where light could not travel freely. Electrons were constantly scattering off photons. Then, as the temperature fell to around 3000 Kelvin, electrons combined with nuclei to form neutral atoms. The universe became transparent, and light could finally stream freely. That ancient light is what we detect today as the cosmic microwave background radiation, a faint glow filling the entire sky, the afterglow of the Big Bang itself. This radiation has been stretched by the expansion of space into microwave wavelengths. Tiny variations in its temperature map the seeds of future galaxies. Without the Big Bang and this precise sequence, no stars, no planets, and no life could have ever formed. The universe was now a vast, cooling sea of hydrogen and helium gas, with gravity ready to pull it into the first structures. After the cosmic microwave background formed, the universe entered a period known as the Cosmic Dark Ages. For millions of years, it was filled with neutral hydrogen and helium gas, with no stars shining yet. Gravity, however, was at work. Slight density fluctuations, tiny ripples from the early universe, began to grow. Over the next 100 to 200 million years after the Big Bang, these gas clouds collapsed under their own gravity. When the cores became hot and dense enough, nuclear fusion ignited. The first stars were born, massive, short-lived giants hundreds of times larger than our Sun. These population, 3 stars were made almost entirely of hydrogen and helium. They burned furiously and died in spectacular supernovas, forging the first heavier elements like carbon, oxygen, and iron in their explosive deaths. These elements seeded the next generation of stars and planets. As stars clustered together, the first galaxies began to form around 400 to 800 million years after the Big Bang. The universe was now lighting up. Ultraviolet light from these early stars and active galactic nuclei started ionizing the neutral hydrogen, a process called reionization that cleared the fog and allowed light to travel farther. Our own Milky Way galaxy started forming roughly 13 billion years ago as smaller proto-galaxies merged. Today it contains over 100 billion stars, vast clouds of gas and dust, and a supermassive black hole at its center. The formation of stars and galaxies was not random. Dark matter, an invisible substance that makes up about 27% of the universe, provided the gravitational scaffolding that pulled ordinary matter together. Without dark matter, galaxies as we know them might never have formed. By about 1 billion years after the Big Bang, the universe looked more familiar, filled with emerging galaxies, shining stars, and the building blocks of future solar systems. The stage was now set for our own cosmic neighborhood. Zooming in from the vast cosmos, we arrive at one ordinary yet extraordinary galaxy, the Milky Way. Our home galaxy is a barred spiral, about 100,000 light-years across, containing between 100 and 400 billion stars. It formed through mergers of smaller galaxies over billions of years. Starting around 13 billion years ago, the Milky Way has a bright central bulge packed with older stars and a supermassive black hole called Sagittarius A*, millions of times the mass of our Sun. Spiral arms wind outward, rich with young stars, glowing nebulae, and dense dust clouds where new stars are still being born. Our solar system lies in the Orion Arm, about 26,000 light-years from the galactic center. This location is relatively safe, far enough from the dangerous radiation near the core, yet close enough to benefit from the galaxy's resources. The Milky Way is not static. It rotates, and it is on a collision course with the Andromeda Galaxy in about 4.5 billion years. The two will merge into a new elliptical galaxy. Stars in our galaxy have different generations. The oldest are metal poor, formed from Big Bang material. Later generations, like our Sun, contain heavier elements forged in previous supernovas. This recycling of elements is crucial. Without it, rocky planets and life as we know it could not exist. The Milky Way is just one of billions of galaxies in the observable universe. Yet it is our gateway to understanding cosmic evolution. Studying its structure, rotation curves, and stellar populations helps astronomers map dark matter and unravel the mysteries of galaxy formation. About 4.6 billion years ago, in one quiet corner of the Milky Way, a giant molecular cloud of gas and dust, perhaps triggered by a nearby supernova shockwave, began to collapse under gravity. This was the birth of our solar system. As the cloud collapsed, it spun faster and flattened into a protoplanetary disk with a dense central protostar. Over tens of millions of years, the core of the protostar became hot enough for nuclear fusion to begin. Our sun was born, a stable, medium-sized star that would provide energy for billions of years. In the spinning disk, dust grains collided and stuck together through a process called accretion. Closer to the hot young sun, only rocky materials could condense, forming the terrestrial planets, Mercury, Venus, Earth, and Mars. Farther out, where it was colder, ices and gases allowed the giant planets, Jupiter, Saturn, Uranus, and Neptune, to grow massive. Jupiter and Saturn formed quickly, within the first 10 million years, sweeping up huge amounts of gas. The ice giants formed a bit later. The asteroid belt between Mars and Jupiter is leftover debris that never formed a planet, largely due to Jupiter's strong gravity. By about 50 million years after the Sun ignited, the main planets had largely formed. The young solar system was chaotic, with frequent collisions. A Mars-sized body even slammed into the early Earth, ejecting debris that coalesced into our Moon. This giant impact also helped stabilize Earth's tilt and created the conditions for tides and seasons. The solar system we see today is the result of this violent early period. Comets and asteroids delivered water and organic molecules to the inner planets, setting the stage for life on Earth. Earth formed around 4.54 billion years ago as a molten, chaotic world. Gravity pulled together rock and metal from the protoplanetary disk. Early Earth was so hot that it was mostly liquid. Heavy iron and nickel sank to the center, forming the dense core, while lighter silicates rose to create the mantle and crust. This differentiation gave Earth its layered structure: a solid inner core, liquid outer core which generates our protective magnetic field, thick mantle, and thin crust. During the Hadean Eon, Earth suffered intense bombardment from asteroids and comets, the late heavy bombardment period. Volcanoes erupted continuously, releasing gases that formed a primitive atmosphere rich in carbon dioxide, water vapor, nitrogen, and methane. There was little to no free oxygen yet. A crucial event was the giant impact with Apia, Mars-sized protoplanet called Theia, around 4.5 billion years ago. The collision vaporized parts of both bodies. Debris orbiting Earth eventually coalesced into the Moon. The Moon stabilizes Earth's axial tilt, preventing wild climate swings. And its gravity drives ocean tides that may have helped mix chemicals for life. Over time, Earth cooled. Water vapor condensed and fell as rain, forming the first oceans by around 4.4 to 4.2 billion years ago. Plate tectonics began, recycling crust and regulating climate. These processes made Earth uniquely habitable compared to its neighbors. By the end of the Hadean and into the Archean Eon, Earth had liquid water, a stable atmosphere, and a protective magnetic field, the perfect ingredients for the emergence of life. Early Earth during the Hadean Eon was a hellish place, often called the Hadean after the Greek underworld. Surface temperatures were extreme, with widespread volcanic activity and frequent meteorite strikes. The sky was dark with ash and dust. Oceans may have formed and evaporated multiple times due to impacts. One theory suggests that a steam atmosphere existed before liquid water stabilized. Hydrothermal vents on the ocean floor, cracks where hot mineral-rich water bubbled up, could have provided energy and chemicals for prebiotic reactions. Despite the hostility, these conditions were crucial. Volcanic outgassing built the atmosphere. Comets and asteroids delivered water ice and organic compounds from the outer solar system. The late heavy bombardment, peaking around 4.1 to 3.8 billion years ago, involved Jupiter and Saturn migrating outward, disrupting the asteroid belt and sending debris inward. While destructive, these impacts may have brought more water and carbon-based molecules to Earth. By about 4 billion years ago, Earth had cooled enough for permanent oceans and a more stable crust. Evidence from ancient zircon crystals in Western Australia suggests liquid water existed as early as 4.4 billion years ago. This fiery period set the chemical stage for life. Simple molecules like amino acids, sugars, and nucleotides could form in the primordial soup or at deep-sea vents through reactions powered by heat, minerals, and lightning. Around 3.8 to 4.1 billion years ago, in Earth's ancient oceans, the miracle of life began. Exactly how remains one of science's greatest mysteries. But several plausible pathways exist. One idea is the primordial soup, organic molecules forming in shallow pools or through atmospheric chemistry, energized by lightning or ultraviolet radiation. The famous Miller-Urey experiment in 1952 showed that amino acids, building blocks of proteins, could form from simple gases and electric sparks. Another leading theory points to deep-sea hydrothermal vents. Here, chemical gradients between hot vent fluid and cold seawater could drive reactions creating complex organic molecules. Mineral surfaces might have acted as catalysts. RNA world hypothesis suggests self-replicating RNA molecules appeared first, before DNA and proteins. These could store information and catalyze reactions. The oldest evidence of life includes stromatolites and microbial mats from 3.5 billion years ago in Australia, and possible biogenic carbon signatures even earlier. These were simple prokaryotic cells, bacteria, and archaea. Life quickly began changing the planet. Photosynthetic cyanobacteria started producing oxygen around 2.7 billion years ago, leading to the Great Oxidation Event. This transformed the atmosphere and enabled more complex life. From these humble single-celled beginnings, evolution through natural selection produced incredible diversity over billions of years. All life on Earth shares a common ancestor, the last universal common ancestor, Luca, Earth's unique conditions, liquid water, stable climate regulated by plate tectonics and the carbon cycle, protective magnetic field and ozone layer allowed life to thrive and evolve. We are the result of that 4 billion year journey. Life did not stay simple for long. Over billions of years, single-celled organisms evolved into complex multicellular life. The Cambrian explosion around 540 million years ago saw a rapid diversification of animal forms with hard shells and skeletons. Plants colonized land, followed by insects, amphibians, reptiles, dinosaurs, and eventually mammals. Mass extinctions, like the one that wiped out the dinosaurs 66 million years ago, cleared the way for new species. Humans appeared only very recently in this timeline, anatomically modern humans around 300,000 years ago. Yet in that short time, we have looked back and understood our cosmic origins. We are made of stardust. The carbon in our bodies was forged in stars. The oxygen we breathe came from ancient photosynthesis, the iron in our blood from supernovas. Every atom in us was once inside a star. Our planet is one tiny speck in a vast universe. Yet it is the only place we know where life exists. As we explore Mars, moons of Jupiter and Saturn, and exoplanets with space telescopes, we search for signs of life elsewhere. The story of the universe is still unfolding. Dark energy drives accelerating expansion. We do not yet fully understand dark matter or what happened before the Big Bang. Future discoveries with advanced telescopes and particle physics will reveal more. What we do know is profound. We are part of an ancient, ongoing cosmic process. From the Big Bang to the birth of Earth and the rise of life, every step led to us. conscious beings capable of asking why, and how single quotes. Our journey of discovery continues. The more we learn about our origins, the better we understand our place and responsibility in this incredible universe. As our journey through 13.8 billion years comes to an end, one truth stands out. The universe is not static. It is dynamic, evolving, and full of wonder. From a hot, dense singularity to the rich, life-filled world we inhabit, every chapter reveals the power of physical laws, working over immense time scales. We have seen how the Big Bang set the initial conditions, how gravity sculpted stars and galaxies, how our solar system condensed from a dusty disk, and how Earth became a cradle for life. Each step built upon the last with remarkable precision. Slight changes in any parameter, the strength of gravity, the expansion rate, or elemental abundances might have made our existence impossible. Yet here we are. This knowledge humbles us and inspires us. It shows that science is not just about facts. It is about connecting with the cosmos. Every child looking at the stars is continuing humanity's oldest quest. Today, we stand at the frontier. Missions to the Moon, Mars, and beyond, along with telescopes peering into the infant universe, promise new revelations. Perhaps we will find microbial life on another world, or evidence of what triggered the Big Bang itself. The story is not over. The universe continues expanding, stars continue forming, and life, if it exists elsewhere, continues evolving. On Earth, our actions will determine the future of our own species and the biosphere we inherited. Let this documentary remind you, we are not separate from the universe. We are the universe becoming aware of itself, made from its materials, shaped by its forces, and now capable of telling its story. Thank you for joining this cosmic voyage. Keep looking up, keep questioning, and keep exploring. The greatest discoveries are still ahead.